This is on, right? Okay. So before we start this next session, let me just do one little bit of administrative thing. There's going to be a PLMW dinner tonight at Fujin. Many of you have already received an email from us about this, but regardless of whether you have received an email from us and have already signed up on the Google spreadsheet, we are now going to pass around this sheet, which says if you are registered for PLMW, regardless of whether you are a fellowship student or not, whatever, if you are registered for PLMW, you're invited to the dinner. If you want to come to the dinner, please put your name down. We need an accurate head count for tonight, okay? So I'm going to pass this sheet around during the session. Just put your names down. We'll collect it at the end. All right, so let's get started with this. Oh, yes. What time is the dinner at Sushi? 7. Starts at 7. Any other questions like that? No? Okay, all right, so let's start the next session. So in this session, we're going to have two talks which are slightly more of a background or tutorial nature. So first we have David Van Horn, who is at the University of Maryland, College Park, and he'll be talking about operational semantics.
Thanks, Amal. Okay, so this talk is going to be very much a tutorial. Okay, so there's nothing advanced here. If you've seen operational semantics before, this is going to be largely a review. And if you haven't seen it before, this will be really helpful for understanding the kinds of things that you see in ICFP papers and the kinds of models that Aaron was talking about in his talk. Okay, so what is an operational semantics? It's really a method for defining the meaning of programs by describing the actions carried out during a program's execution. Okay, and there's many different flavors of operational semantics, and the sort of goal of my talk today is to show you an instance of each of these flavors of semantics. Okay. So there's things like evaluator semantics. This is the kind of thing you usually see in an undergraduate course on programming languages where you write interpreters as a way of defining the meaning of programs. There's natural or big step semantics. There's reduction semantics and abstract machines, things like that. So we're going to see all of these things. But what's it actually used for? Well, operational semantics can be used for specifying a programming language. Really, I think the sort of primary use for an operational semantics is communicating language design ideas. Okay, that's why you see them in research papers when we're trying to communicate to other people what our ideas are. When we want to talk precisely, we use semantics to be precise. Okay, and related to that, they're used for validating the claims that we make. Okay, so claims about languages, claims about type systems, things like that. If we want to do things like prove a compiler's correct, we need an operational semantics, okay? Or a semantics, but I'm going to focus on operational semantics today. Okay, so if you look at the proceedings for ICFP, I would guess that at least 50% of the papers have an operational semantics in them. Okay, so I picked somewhat at random a paper from this year's ICFP called Context-Free Session Types. Okay, I don't know much about this paper, but I started looking through it to see where the operational semantics come up and what role it plays in this paper. Okay, so if you look at the contributions and overview of this paper, they say we introduce context-free session types. Okay, whatever that means, whatever those are, right? So this is a paper that's introducing a new type system idea about context-free session types that extends, past ideas on session types to capture the type-safe serialization of recursive data types. Okay, so in that sentence, there's really a claim hidden. Okay, so they introduce a new type system, and they're making a claim that it supports the operation of serialization of recursive data types that's type safe. Okay, so they have a type system that if the type system signs off on your program, then it means that when you go to serialize something that's a recursive data type, it's not going to fail at runtime. Okay, and that's a claim that can be made very precise. Okay, and the way that you would make that claim precise is you would define an operational semantics for your language and what it means to run programs. Okay, so here's the figure from that paper that defines it. Okay, so if you've opened up papers and seen stuff like this and had no idea what's going on, this talk is for you. Okay, so at the end we'll come back to this figure and we'll try to see what's actually going on here. Okay, and they're going to prove something in their paper, which is this type safety result. Okay, so they've got a type system, and if your program is well typed, then they're gonna make two claims about it, right? So they're going to have a theorem in the paper for what's called progress and preservation, and this is typically how you prove a type safety result. So progress says that if the program is well typed, then either it's done computing or it can take a step. Okay, that figure is basically defining what it means for the program to take a step. It can move along in its computation. And preservation says that it maintains its well-typedness as it computes. Okay, and those two facts together give you the type safety. Okay, I'm not going to talk much about type systems in this talk. I'm going to focus on the operational semantics here, but it serves the purpose of validating those claims that they're making. Okay, so we're going to look at a much simpler language than these sort of communicating processes and things that are going on there. We're going to look at things in the simplest setting I could come up with that will show you all of the ideas. Okay, so it's just arithmetic. Okay, this is like the world's dumbest programming language. Okay, 1 + 2 = 3. That's what we're going to do. Okay, all right. So we're going to see the syntax and how we define the syntax of the language, and then we're going to see the semantics in a bunch of different forms. Okay, and that's what we're going to do. So when you define the syntax of a programming language, our programming language here is called A. When you define the syntax of a programming language, you're defining a set. Okay, you're defining a set of expressions that are in the language. Okay, so I'm going to show you 3 ways to do it. So this way is maybe the most tedious way of, I give a bunch of constraints on that set, and I say it's the smallest set that satisfies these constraints. Okay, and it's an implication here. So the way to read this is, if I is an integer, then I is in the language. Okay, so all of the integers, they're in the language A. If E is in the language A, so if we have an expression, E, then taking the predecessor of E, that's also in the language. Okay, and likewise for successor, and if you've got 2 expressions, E1 and E2, then you can put them together with the plus constructor. Okay, so this is defining the terms in my language. I should have mentioned this already, but if anyone has questions, stop me during the talk. Okay, we don't have to wait till the end. If you're confused about anything, stop me and we'll go through it. There's nothing complicated here. There's just notation that you probably haven't seen before. Okay. All right. So what you'll most likely see for defining syntax in papers, which I think is a little more readable, is a grammar. Okay. So this is generating that set. So I'm saying here that I could be an integer here, and that E's are either integers, predecessors of expressions, successors, plus and multiply. Okay? So alternative way of defining exactly the same set of expressions. And then the next one I'm going to show you is to use inference rules. Okay, so if half of the papers at ICFP have operational semantics, I'd say 70% of the papers have some inference rule in them. Okay, you'll see stuff like this all the time in programming language papers. Okay, and it's really just a shorthand. A lot of what I'm going to do today is just explain away a bunch of shorthands that we use as a community to compactly communicate things to each other. Okay, and inference rules are just one of these nice shorthands. Okay. So you'll see this bar, and you'll see stuff above the bar, and you see something below the bar. And what it's a shorthand for is defining something by an implication saying that if the stuff on the top is true, then the thing on the bottom is true as well. Okay? So you've got hypotheses on top and a conclusion on the bottom. Okay, so if I wanted to define by a set of inference rules my language, I would say something like this. If you've got an integer, that's in the language. If you've got an expression, the predecessor of it is in the language, and so on. And this is really just a kind of different notation for that first definition that I gave you. Okay, but we're going to see a bunch of inference rules, so it's good to understand them in this simple setting here before we move on. Okay. The nice thing about inference rules is that you can construct proofs of the things. Okay, so here, if we wanted to know if this expression I have up here is actually an expression in my language, A, then you can construct evidence for it by making this tree. Okay, where each bar in the tree is an instance of those rules that I showed you. Okay, so if you can construct a tree that concludes with the thing that we're trying to show, and you can look at this and verify that each one of these is an instance of those rules I showed you, then that's proof that this is an expression. Okay. All right. So the first kind of that's the syntax, right? That's what programs look like and what they are. And now we're going to talk about what they mean. Okay, so a really simple form of semantics that I can define is called the natural semantics. And it's a binary relation that relates expressions in my language to their value, which are going to be integers here, right? Because if you have a arithmetic expression and you evaluate it, you should get some integer here. Okay, and as an example, I have an expression here, and that's what I would like it to evaluate to, 7. All right, so 4 plus 2 plus 1 ought to be 7. And I'm going to define it using inference rules, just like we saw how how terms were expressions were defined. Okay, so I've got a set of rules here, set of inference rules, and there's one for each kind. There's one for each kind of expression. Okay, so integers, well, they just evaluate to themselves. 5 evaluates to 5. Okay, if you've got the predecessor of an expression, well, you have to first evaluate the expression and get an integer back, and then you subtract 1 from it, and that's what predecessor of E means. Okay, or in other words, if E evaluates to I, then predecessor of E evaluates to I minus 1. Okay, so it's all pretty simple here, right? How do you do predecessor? You subtract 1. How do you do successor? You add 1. How do you take the plus of two things? You add them together. Okay. Now there's something that I think is maybe a little confusing here, right? Which is I wrote things over here like I plus j when I was defining plus, and really, if we wanted to be a little more careful about it, right? I don't want you to think that this is some compound piece of syntax here, right? This is just a single integer, okay? It's just some number k that's the sum of those two numbers, and that's what we get back here, okay? All right. And again, we can construct proofs of things being in this relation, okay? So here's a tree that's just showing that this expression evaluates to 7, and you can verify that each part of the tree is an instance of those rules that I showed you. Okay? So that's the natural semantics. It's just a binary relation, and it was a binary relation defined as a set of inference rules. Okay, we can talk about the evaluator semantics, and the idea behind an evaluator semantics is you write an interpreter in another programming language. All right, so here I'm writing an interpreter in OCaml for my language. So I've got a data type for representing expressions, and then I've got a function here that takes in an arithmetic expression and gives you back an integer. Okay? And you can see that the type of this function which is expressions to integers, is close to that idea of the binary relation from expressions and integers. Okay, the difference here is that this is a function that computes what the integer is given an expression. Okay, so there's a close correspondence with my function here and those rules that I showed you, right? Namely, the hypotheses show up over here, and then what we get from evaluating those things is what the conclusion of evaluating that is there. So they're in a one-to-one correspondence here. Okay, and the nice thing is we can do things like run programs now. Okay. All right. So now I'm going to show you a different flavor of semantics. Okay, and this is called a structured operational semantics, sometimes called a small step operational semantics. And the idea here is really just a refinement of the idea that we've seen already. Okay, so we started with a relation that tells you for any given expression what it means, and this is going to tell you how the computation proceeds to get you to that answer. Okay. So it's another binary relation, and it's going to be, but it's no longer between sort of expressions and their final result. It's going to be it's going to be a relation between expressions. And the idea is that two expressions are related if in one computational step you get from one to the other. Okay, so here's that same example. Plus of 4 successor of 2. And so if I'm defining this relation, what I would like is that in one step, I get to plus 4 and 3. Okay, so I'm just doing a sort of piecemeal computation here. And then from that expression, in another step, I could go from plus 4 and 3 to 7. So it's spelling out each of the steps that the program takes as it runs. Right? That's the idea here. Question? Yeah.
So you mentioned it only needs to be a relation between two expressions, right? So why not go the other way? Why not say 4 is a successor of 3, and then why not go the other way and just never compute anything? Is that said in the definition?
That's in the definition. Yeah. Okay. We'll see it in the definition that there's a kind of directedness. That's why the arrow points in one direction. That you can't. I mean, the way that it's defined, things run towards simpler expressions. Okay. Okay. So we're going to define this relation in using inference rules, just like before. And there's something I want to point out here, right? So each step of the computation now, there's going to be a proof that sort of justifies taking that step. Okay. And one thing just to observe here is that it's not the case that this expression is related to 7, okay? Because in one step, you don't get to 7, okay? So just to be clear about the relation we're talking about, it's only relating things that in one step reach each other, okay? Okay, so there's sort of two parts to the definition here. One is going to be a set of reduction axioms that say, okay, if you've got the predecessor of an integer, okay, this is not an arbitrary expression here. This has to be a literal integer. Then you can reduce that expression by subtracting 1 off the integer. Okay? That's not the way that the natural semantics was defined. Yeah.
So I noticed in this one on another slide, you kind of just use the letters
Mm-hmm.
to denote integers versus expressions.
Yeah.
Is there any other way I'm supposed to be able to tell what you mean?
Yeah, that's a great question. So these variables that I'm using here, I define them in the beginning, by this grammar, different definitions for what the variables range over. Okay, and as a convention, when I write rules like this, I mean that I has to be something drawn from that set of things that it ranges over. Okay.
Oh, like did you specify J, for example?
J, I didn't specify. The way I would have done it is in the grammar, I would have said I or J is blah, blah, blah. Yeah, that's right. So the J I didn't define. It's meant to be just an integer. Okay. But this is a way of sort of restricting what I'm talking about here. It's not any expression, right? I can't be an airplane. It has to be an integer, all right? Okay. So I've got these sort of the four simple things that just handle when you've got literal integers. Well, you can add and subtract, right, and multiply, things like that. And then you've got these rules that talk about reducing inside of expressions, okay? So if you've got the predecessor of some expression, and that expression can take one step to some other expression e prime, then pred of e can step to pred of e prime, okay? And there's one rule sort of, okay, so for things like predecessor and successor, there's one sub-expression, and if it steps, the whole thing takes a step. And then things like the binary constructors here, right, you can either take one step on the left sub-expression, or you can take one step on the right sub-expression. So that's the one about the left. This is the one about the right, okay? And really, it's just saying that you can reduce inside of the expressions here, okay? So there's a bunch of rules here, but there's nothing interesting going on, right? It's just saying that you can reduce inside of expressions. So sometimes this is called the compatible closure. This is another kind of shorthand, right? If the idea is you allow reduction inside of any sub-expression, well, then all we really need to see are these rules, and then you say, okay, and then take the compatible closure of that relation, right? Or we could spell them out like I'm doing here, okay? And like I said, so each step of the computation, there should be a proof justifying that step. And now one thing that you might anticipate here is that there's many different ways that you can reduce an arithmetic expression to get to the final answer here. And this relation models that, okay? So if you've got this expression that I have here, right, it can take two different steps to two different expressions, okay? Now, it should be the case, I mean, here we sort of expect that if they go to different expressions, they'll eventually come back together, which is just a property of a language, right? So that's the kind of claim that you might make about your language, that no matter which way you do the reduction, eventually you get back to the same answer. And that's a property that's true in for this simple language. It's not true for richer languages. Okay, and then we can then define in terms of the one-step thing something like takes 0 or more steps. Okay, so what this star means is this is a relation that's derived from the one-step relation that says in 0 or more steps I get to this thing. Okay, so if you can get there in one step, you can get there in 0 or more, and in 0 steps you can get to yourself. Okay. Okay, this is also just the reflexive closure. And if you can get from something to something else, and from that something else to yet another something else, then you can get from the starting thing to the ending thing there, okay, which is just the transitive closure. Okay. And then a claim that I'll make about the relation between these semantics is that in our natural semantics, if you evaluate something and you get an integer, well, it should be the case that that's also in the relation by taking 0 or more steps. Okay? So from this, you can see that the small step relation is really just a kind of refinement of the natural semantics here, right? It's telling us more information about the intermediate steps. Okay? But if we want to recover just what the final answer is, that's also in the relation here too. Okay? Okay, so now I'm going to show you reduction semantics, which are really just a kind of stylized way of doing the one-step, the structured operational semantics that I've shown. So if you think about each of these proofs, right, if I say that something steps to something else, what does the proof of that look like? It always looks, it's not a tree, it's a list. Okay, there's no branching in it. Okay, and it always ends with something that relates by one of those axioms. So I gave that thing a name called A. So, the things that deal with successor and multiply, right? It always ends in one of those. And then the rest of it is all of those contextual rules which let you reduce inside of sub-expressions. So you build up this whole big tree just to say, oh yeah, that sub-expression here reduced to that thing there. So the idea here is that we can have again a more compact notation for this. Okay, these are those axioms. Okay, we can have a more compact representation of that by defining a grammar of contexts here. Okay, so a context, intuitively, it's just an expression with a hole in it. Okay, so you've got an expression, and you've ripped out some sub-expression. Okay, and you've got your finger on where that sub-expression was. Okay, so you've got this grammar, and this is just, everywhere that E occurs in your grammar here, you could say, oh, I could have a context there, and it bottoms out with being a hole written with this little square here. And then I have my set of axioms, and then I just have one rule that says, okay, if you have, okay, so I have to tease apart what this means. But if you've got some expression in some context C, and that expression reduces by the axioms here, then I can reduce the whole expression, okay, with keeping the context the same. Okay, so what this means, this notation here means, is you've got some expression that it is composed of a context with some expression inside the whole of it. Okay, and it's overloaded here. Okay, it's overloaded to mean I've got those two things and I want to put them together. Okay, which gives you back an expression, right? I've got a context and I'm plugging the expression into the whole. Or it means I've got an expression and I want to decompose it into those two things. So here on the left, we're saying you've got something that decomposes into a context with an expression inside of it. And then on the right, we're saying, well, take the inner expression here, take a step with it, and then plug it back in. Yeah? That's the only thing you can do, is you can plug expressions into it, right? So you can decompose expressions into contexts and inner expressions, and then you can plug them back together. Now, the question of what you can do with them is a good one, and we'll actually see some of this in the future. That I introduced this as just a shorthand, and so far it is. But there are opportunities for us to do new things now that we have a handle, right? We've given a name to the context here, and we can do stuff with it. Okay, so we'll hopefully see some things we can do there. Okay. Coming back to this idea that there are many different ways that you can reduce programs, sometimes that's not what you want. Okay. Sometimes you want to talk about a canonical way to go from an expression to a final answer. Okay, so this is known as a standard reduction. This is a strategy that is of all of the options we have to go from the expression to the answer, let's pick a particular way of getting there. Okay, so here's one way to sort of canonicalize the reduction of expressions. Okay, so either you take one of those reduction axioms, right? 1 + 1, so on. If you've got a predecessor, well, you do a canonical step on the inner expression. Same for successor. Now, plus is going to work differently. So plus says that if you've got a value, I should have written I here. Okay, so that's just a typo. But if you're already done with the thing on the left, only then should you be able to reduce the thing on the right. Okay, so we restrict things here to say that it has to already be fully reduced to an integer, but on the left there's no such restriction. Okay, so there's a strategy here, and the strategy is evaluate the sub-expressions left to right. We could write different rules if we wanted to go right to left. Okay. Okay, but that's really we're just nailing down a canonical way to reduce. Yeah.
Do you say the word canonical, we imagine that there's only one way to reduce
Right.
one expression.
Right.
So if you write it this way, the expression
Right.
So do you have to prove for that?
That's right. So that's that is implied in my is saying that it's canonical means that there should now be just one way to get from expressions to integers, and yeah, I should back that up with some proof that that's the case, which means proving that this relation is a function.
If there is such a proof in the place, what's the difference between the standard reduction with the small step, like one step?
Okay, so well, so here, let's see. Maybe I'm not fully understanding the question. Uh, so here I'm defining a different relation that is a subset of my one-step reduction relation that lets me reduce anywhere, right? And if I wanted to claim that it's a canonical strategy, I would have to show that it is, in fact, there's only one way. And I probably also want to show something like if I can get there by any strategy, maybe I can get there by the canonical strategy as well. Okay.
But also, he had an example earlier that showed that there was multiple ways to reduce
Right.
a particular term, so it wasn't canonical.
So basically,
There was another example.
so basically using the notation of standard reduction implies that we want to have a proof that it's a
That's right. So there's properties of this relation that I'm claiming but not proving here, but that we should actually make sure is true. It's pretty simple to see that none of and the way that you could show it here is you just look at the left-hand sides of these of this relation here, and you see that actually none of these rules overlap. Okay, so you do some case analysis on all the rules, and you show that they don't overlap. So at most, one of them can apply at any point, and that's an easy way of showing that it's a partial function. Okay. Okay, so here we're back to sort of, you've got the axioms, which are the things that sort of really matter, and then you've got all of these rules, which are really just telling you about where you can apply the axioms. And we can also represent that grammatically, all of those rules grammatically, with a different notion of context, so which we'll call evaluation context. Okay? So this is just a subset of those contexts that we saw earlier where there's some restrictions. Again, that should be an I, not a V, but there's some restrictions on what an evaluation context is here. So the way that you can read these, so you'll see evaluation contexts a lot in papers. And the way that I read them is it's just telling you where you do the reductions in order, okay? So when you are doing, when you've got a plus expression, you do the left side first, okay? That's what this production in the grammar is saying. And when you are done on the left, then you do the right, okay? So you can read off this ordering from the grammar here, okay? And we should hope, it's the case here that these relations, if you can get to an answer, you can get there in the standard way, and vice versa, okay? And this property also won't be true in richer languages. Okay, and we can also talk about more of like a machine model. Okay, so the previous models that we've seen, they've been fairly high level, right? One is defined so one was the natural semantics, and the other was these various forms of these reduction semantics. But if we wanted to actually implement this, well, we've already seen one implementation, right? We saw the OCaml implementation. But if you look at that, it's a recursive OCaml function, okay? So if you think, I want to get down really low level here, right? Most of the architectures we have, they don't have higher order functions and recursion and things like that. So maybe we want to get some lower level view of how you would implement this. And we can give a semantics for that low level view of things as well. Okay, so I'm going to make a stack machine here. Okay. Okay, so the frames of my stack, they're just going to be very simple evaluation contexts. Okay, it's not a recursive definition here, right? There's no f occurring over here, right? So it's either, the frames are either I need to do predecessor, I need to do successor, right? I need to evaluate the right side of a addition, yeah, or I'm done. I'm done with the left side, and so on. Okay, and then what the stack is going to be is just going to be a list of those things. Okay, so there's a relation here between my grammar of evaluation contexts and the frames of my stack and my stack machine. And I'm going to define a set of terms that I call serious terms, which are just expressions that aren't integers. Okay, serious terms meaning they've got to do some work. Okay, so there's three actions that my machine can make. So the machine operates on pairs of expressions, an expression and a stack. And you can either have an expression that, okay, so the one case of what my machine can do is it could take a computational step because I've got an expression that's ready. I've got 1 plus 2, and I want to turn that into 3. Okay, so the stack stays the same, and my machine takes one of these reduction steps. Okay, or it could be that I've got an expression that is like the predecessor of some serious term. So then I'm going to push a frame onto the stack and focus on doing the work on that serious term. What this is really implementing is that idea of decomposing the context, the program into a context and an expression that you're going to reduce, right? And it's building up that context in a kind of inside-out way. So if you look at that list of frames, you can, if you read it off, beginning of the list to the end of the list, then that's just looking at the context from the innermost part to the outermost part. Okay, so there's a correspondence there between the stacks and the evaluation context. Okay, so there's the pushing operations, and then there's the popping operations, which is when you're done here, when you've got something that's fully reduced, but you've got stuff on the stack that you need to do, well, then you put them back together. So this is implementing the composition of the context here. Okay, so the stack is really just doing the decomposition and composition operations with the context. Okay? And there's a claim here about the correctness of my machine. Right, that if in the empty context you get to some integer, then it's got to be the case that by a standard reduction, and remember we have all these other relations with all the other semantics we've seen, so it's related to all of them as well. Okay, so that was it for arithmetic. And I'm going to show you another cool language feature that you may have heard of called functions. We are at ICFP after all, so I'll show you that quickly and just go through sort of the same semantics, seeing this other language feature, added on. And if you wanted to add other language features, right, you can do it. And you could do the machine semantics, the natural semantics, and so on. And really, it's just like the arithmetic stuff that I showed you. As my advisor would say, it's just more cheese on the pizza, right? It's still a pizza, and it's got all the same basic ingredients. There's just more of it, okay? Okay, so if we wanted to add functions, we would add syntax for them, like applications and lambda terms and variables. Okay, I'm going to pick up the pace here a little bit, okay? And now I've got this idea of a value, which can either be an integer or a function. Okay. Now, function application here is going to be defined in terms of substitution. So when I apply a function, the way that we think about what happens is we substitute the argument in for the formal parameter. So this is parts of the definition of substitution, and the tricky part is what do you do when you're substituting an expression in for x in the body of a function. Because you've got to be careful when e contains a variable named x prime here. Okay? And I'm not going to show you how to resolve the tricky part of the definition here, right? It's not important unless you want to get it right. And it's not so easy to get it right, okay? So here are the natural semantics. When you've got an application, you evaluate E0. Hopefully you get a function back. And then the whole thing evaluates to V if you take the body of the function and you substitute E1 for X in the body there and get some value V back. Okay, and you should maybe observe here that this is doing a call by name. This is a call by name semantics, because we didn't say anything about, E1 first having to evaluate to a value. Okay, if we wanted that semantics, it's just a different rule, right? Saying that E1 has to first evaluate to a value, and then you substitute the value for X. Okay. The reduction semantics, we're going to have a new axiom, which says if you've got a function that is being applied, okay, so again, it's about you've got these things ready to go, then you can take that reduction step, and then you have some new contexts, and you say that if either by the arithmetic axioms or my new beta axiom, you take a step, then you can take a step in context. Okay. If you want a call by value reduction semantics, well, then you restrict the beta axiom to talk about values, and you use that. Okay. If you want to talk about a standard strategy, well, then you want to talk about evaluation context and do a restricted set of the contexts in which you allow reduction. In particular, you don't allow reduction inside of function bodies. Okay, in the call by name case, and this is the call by value case where you want to enforce that the left sub-expression in an application is evaluated before you evaluate the right sub-expression. Okay, abstract machine here is going to be just like before, okay? Okay? Okay, so I'm basically out of time. I wanted to show you things like exceptions. Okay, this is something where using that evaluation context notation is really quite nice, because we can do things like talk about, okay, so I didn't define this, but we can talk about a set of evaluation contexts which don't contain tries in them. And then I can make an axiom that says you throw that part of the context away. So by giving something a name, I can do things with it, like throw it away. Okay, so if I wanted to have a nice definition of how exception handling works, this is a nice way of doing it. Okay, there are other kinds of control operators that I could use that also lend themselves nicely to being defined in terms of evaluation context. Okay, so we've seen some operational semantics and what they're useful for. Okay, and if we come back to that paper I mentioned, right, at least some of this should be a little more understandable, right? So right up there's that beta axiom that we talked about. Okay, so they have beta, they've got, deconstructing pairs, so they've got pattern matching. Okay, so if you wanted to know how you would write down the semantics for pattern matching, they've got that. They've got recursion. Okay, look, here's that contextual evaluation rule that we saw. Okay, here's how new processes are forked, things like that, right? So we can understand in a very crisp way what's going on in their paper. Now, for the things, so some of the stuff is standard stuff that we saw, and then some of the stuff is really relevant only to what they're talking about in that paper, and we'd have to go read the prose to understand what's going on there. Okay? All right. Thank you. Are there any questions? Yeah.
Can you use natural semantics when you have no termination?
Okay, so that's a good question. So when we're talking about arithmetic, every expression produces an integer, right? You can just run it, and you're guaranteed you're always going to get an integer back. Once we introduced functions and applications, that was no longer the case. So the question is, can we still define things in terms of the natural semantics? And the answer is yes, you can. But that relation isn't going to tell you anything about programs that don't terminate, because there's no answer that you get to. So this is something that's nice about the small step stuff, is you can talk about each of the steps that a program that runs forever goes through. So when you prove things like type safety, you want to show that even programs that run forever don't eventually do something bad there. So usually it's the way that you prove it is you define a small step operational semantics there. Okay, so I'll be around for the rest of the day. Feel free to come up and ask any other questions. And thanks a lot again.